if for the nonlinear deformation, the curvature definition with the that one will change. We'll add some high order term. Okay. Okay. Note. Okay. In mathematics, the curvature of arc length equal definition of a d tangent vector change of the s. Okay. Yeah. Yeah. And it's like this. Okay. And this is my arc length, and at some point I have a tangent vector t at s. And after some distance, I have a tangent vector t s plus delta s. Okay. So this will be as a limit delta s approach to 0, and the t s plus delta s vector such that t, the tangent vector at s, divided by ds. And as this ds delta s, and as delta s approach to 0, that's what the definition of a curvature. Okay. This is large and equal to 0. So you don't have suppose the curvature have positive things. And in plane, in 2D, okay, 2D, x, y. If I have a curve as y of x, okay, y of x, and the curvature at s is equal to dy dx squared over 1 plus dy dx squared and 2/3. Okay, so this is an original theory. Okay, or we can write a y double prime over 1 plus y prime squared and quarters. If y prime is smaller than 1 and y prime squared equal to 0, okay, small. So this will be approximately y double prime 1. So that's why for small dy dx or dw dx, your curvature is close to double prime. Okay, that's from the mathematical theory. Okay, it can be proved. Okay, go back to check your mathematics books. You can find it. 2/3 prime square. Okay, that's for nonlinear relation for curvature. Okay. Okay, so after we got this, then we can get the relationship between the moment, because I have shown moment is integration resultant of the internal normal stress, right? So let's see what we can get. Yeah. Okay, so for a beam with a cross section, this is x-axis, this is z-axis, y. Okay, and at this positive x, positive y, and positive z, this area, we have stress, is dA. Okay, so this is it's dA. Okay, and with z coordinate. And this cross section, we have anyway. So here, this force sigma x times dA is a force, right? And the moment about y-axis. Okay. So we have a moment equal to the dm. Dm created by the sigma x at z with the dA area times the moment arm. So this is a force times moment arm is the axis related to the y. Okay? And I integrate dm will be equal to m. Integrate sigma dA x dA times z. All right? And dA, okay? Or we can write this, this equal to Young's modulus times epsilon x. Okay? And this also equal to z, curvature. So this integration will become an integration of E k z square dA. Integrated, okay. Cross section, right? Then this constant for this x coordinate, so I can take it out E and curvature take out, and with the integration of dA times the z square. And what is definition? This equal to I. That's equal to I. All right? So that's we have the moment equal to E k I, or we write to E I curvature. Okay? And this we call the bending rigidity. So how easy this beam can be bent depends on the bending rigidity. Okay, if you want to create how much curvature, then you need the moment equal to the curvature you want and apply the bending rigidity of this material, the beam. That's the moment you require to apply to cause this value of curvature. Okay. And this is the linear relationship between the curvature. But in the future, our material may be nonlinear. So, for example, if the stress-strain relationship, this is a linear. If your stress relationship is nonlinear, okay, then it's function of this. That means your theory here will be a nonlinear function of curvature. Okay? Then you will get the moment your sigma x will equal to function of epsilon x equal to function of z curvature. Right? And for nonlinear, maybe this is a nonlinear function of curvature relationship. Right. Okay, now so far we have for this, okay, let me continue. Okay, the summary, what we have. summarize. For Bing theory, with a distributed lateral loading Q function of x, and this is my put in the middle x-axis, okay, or neutral axis, okay, and this is my W. We have the v dx equal to minus q, okay. We have a dm dx equal to v. We certainly have a dm double square equal to minus q, okay. And we also have a moment equal to okay, maybe this is a curvature, is equal to minus dw dx squared. Okay? And the moment is equal to ei curvature. Okay? And we also have a strand equal to z curvature. Okay? And moment, maybe later. Okay? Moment is equal to definition of a sigma x dA times z integrate. And this sigma x equal to E epsilon x. And this will come is the EI curvature. Okay.